Now, today I'm going to talk about the fast sampling and counting KSAT solutions in the local Lemma regime. I'm Wei Min from Nanjing University. This is a joint work with Heng Guo from University of Edinburgh, my advisor Yitong Ying, and Chihao Zhang from Shanghai Jiao Tong University. Okay, our work centers on a CNF formula phi, which is a conjunction of one or more clauses. We use V to denote the set of the variables and C to denote the set of the clauses. A set solution is an assignment of variables in V such that all the clauses are satisfied. Now in this example, the V is the variable x1, x2 to x5, and the C is the three clauses. There are two fundamental computational tasks for CNF formula: decision and counting. Decision is to determine whether that solution exists. That is, we assign each variable either true or false, such that all the clauses are satisfied. Counting is to estimate the number of different solutions. Both problems are very fundamental in computer science, one being NP complete, the other being SHP complete. We focus on a specific class of CNF formula. Each class contains k variables, and each variable belongs to at most d clauses. Such a CNF formula is called the KD CNF formula. Now, in this example, each clause contains three variables, and each variable appears in at most two clauses. For example, let's look at the variable x2. X2 appears as the negation of x2 in the first clause and x2 in the second clause. So this example is a 3-2 CNF formula. Now, by Lová's local lemma, when k is roughly greater than log d, a set solution must exist. Eldishh and Lová's proved that if each variable in V takes true or false uniformly and independently, then with a positive probability, all the clauses are satisfied. This implies the set solution must exist. As we can see, this proof is non-constructive. Later on, Morse and Eldishh came up with a famous algorithm that constructs a specific KSAT solution in linear time under the same condition. Our work focuses on the sampling and counting problems. The input is a CNF formula phi. When sampling, the algorithm needs to draw a random solution that is almost uniformly distributed over all set solutions. Specifically, we use mu to denote the uniform distribution over all KSAT solutions. The algorithm should output a random solution x, such that the total variation distance between x and mu are bounded by a given bound epsilon. The counting problem requires to estimate the number of different solutions. The algorithm should output a number z hat, which is an epsilon approximation to z. Here z denotes the number of KSAT solutions. The sampling and the counting problems are closely related. If we can perform the almost uniform sampling, then by some reductions, we can do approximate counting. So in the rest of this talk, we will focus mainly on the sampling problem. Now let us review some previous works. Now Hermer et al. Proved that if k is roughly greater than 2 log d, then the Markov chain Monte Carlo method draw approximate samples in polydk times O n log n time. But his algorithm only works for monotone CNF. Here, monotone CNF means each variable appears positively in every clause. The monotone CNF is also called the Hilbert graph independent set in other papers. Guo et al. Came up with a partial rejection sampling algorithm that sample CNF solutions in linear time. However, their algorithms still have an extra requirement on the CNF formula. Each clause, for two clauses, they neither do not share any variable or share at least S variables. So it still works on a specific class of CNF formula. Moichel made an important breakthrough in this research line. He gave a new algorithm based on linear programming. The algorithm is quite different from the traditional sampling techniques. His algorithm runs in time n to the poly decay. So to have a polynomial time algorithm, it still requires d and k to be the constant. But Badikova et al. Proved a lower bound result. They show that if k is smaller than 2 log d, the sampling problem is NP hard. So there is a very important open problem in this research line. For general CNF formula, would there be a sampling algorithm that achieve the following 2 points at the same time? First, push the threshold down to k roughly greater than 2 log d. If so, the upper bound will match the current lower bound and will obtain the optimal regime for sampling and counting CNF solutions. Second, improve the running time to the poly decay times O2 m. If so, even if d and k are unbounded, the running time is still polynomial and the dependency to m is almost linear. In this work, we partially answered this open problem by giving a new algorithm based on the Markov chain Monte Carlo approach. Our algorithm works for general CNF formulas. We require k to be roughly greater than 20 log d. This makes our algorithm very fast. The exponent of m would be very close to 1. We emphasize that our algorithm only requires k to be roughly greater than 20 log d. We do not have any extra requirement on the CNF formula. Now, more formally, we actually prove the following main theory. For any sufficiently small parameter zeta, if k is greater than 20 log d plus 20 log k plus 3 log 1 over zeta, then we have a sampling algorithm in time O2 d squared k cubed n to the 1 plus zeta, and we also have a counting algorithm in time d squared O2 d cubed k cubed n to the 2 plus zeta. If the parameter zeta becomes smaller, the gap between k and 20 log d plus 20 log k plus 3 log 1 over zeta would become larger, and this condition becomes less confined, and our algorithm becomes faster. The sampling algorithm the running time of the sampling algorithm would approach to linear, and the running time of the counting algorithm would approach to the quadratic. Our main contribution in this paper is a new algorithm for sampling CNF solutions, while the counting algorithm is obtained by the simulated annealing reduction. So in the rest of this talk, we will mainly focus on the sampling algorithm. So let's have a look at the sampling algorithm. Before describing our approach, let me explain why the traditional approach fails in solving CNF problems. Perhaps the most well-known Markov chain Monte Carlo algorithm is the global dynamics, which is also known as the Gibbs sampling. The algorithm starts from an arbitrary set solution, then randomly updates the solution in t steps. In each step, the algorithm picks a variable uniformly at random, then resample its value conditioning on the assignment of other variables. Now, for example, if we pick the variable x5, now x5 incident to 2 clauses, the second clause and the third clause. Note that the second clause is already satisfied by x7, and the third clause is already satisfied by x4. So x5 can choose its value to be true or to be false uniformly at random. However, if we pick the variable x2, then to satisfy the first clause, the value of x2 must set to be false. This because the first clause because the x1 and x3 cannot satisfy the first clause. Now, in this situation, we choose the variable, but we cannot change its value. This issue will cause a big problem in sampling CNF solutions. As we can see, the global dynamics is actually a random walk over solution space. Given the current solution, each time we pick a variable and update this variable to update the current solution to a new solution. But in this situation, we choose a variable but cannot change its value. This means that we cannot update our solution to a desirable one using this update method. Now, to illustrate such a barrier, let me show you a small example. Now, let's consider a CNF formula phi, which contains k variables, x1, x2 to xk, and also k clauses, c1, c2 to ck. Now, consider the following CNF formula. Well, the first clause is the negation of x1 or x2 or x3 or xk. The second clause is the x1 or the negation of x2 or x3 or xk. In general, the ith clause contains the negation of xi. Now, let's consider the assignments of variables. If only x1 takes the value true, then and all other variables takes the value false. This assignment is not a satisfying assignment because the first clause cannot be satisfied. And similarly, if only x2 takes the value true, then the second clause cannot be satisfied. So in general, if only one variable takes the value true and other variable takes the value false, this assignment is not a satisfying assignment. But on the other hand, if all the variables takes the value false, then we will have a satisfying assignment because C1, C2 to CK will all be satisfied by the all false solution. Now suppose the global dynamics starts from the all false solution. Each time we pick a variable, but we cannot flip its value because it will give us an unsatisfying assignment. So the global dynamics will always stay in the all false solution, and it cannot converge to the other solution, and it cannot reach other solutions. So the algorithm cannot converge to the uniform distribution over all satisfying assignment. Actually, the global dynamics represents a very important class of sampling algorithm. This class is called the local Markov chain. The local Markov chain is one of the most fundamental approaches for sampling. It has successfully solved many problems. For example, the uniform graph coloring, the weighted independent set, the EC model, and the base of the matroid. The crucial point for this approach is how well the solution space is connected. If the solution space is well connected, the chain will converge rapidly. If the solution space is not well connected, the chain will converge slowly. But for CNF problems, the solution space can be disconnected, which means starting from some initial solution, it is impossible to reach the solutions in other components. And I remark that in the worst case, there can be exponentially many connected components. So the Markov chain cannot converge to the uniform distribution. This connectivity barrier makes the powerful Markov chain method useless in sampling CNF solutions. And previously, Markov chain Monte Carlo approach only works on monotone CNF because the monotone CNF do not have such a connectivity barrier. And other works came up with some non-Markov chain approaches. However, they only works for restricted class of CNF formulas. The partial rejection sampling works only for CNF formulas with a lower bound of intersection, and the linear programming proposed by Moichel requires D and K to be constant. So an open problem is can MCMC approach bypass this connectivity barrier? The main contribution in this paper is a new technique to bypass such a connectivity barrier for sampling synapse solutions. Our technique is a projection. We project from a high dimension to a lower one to improve the connectivity. Now, the principle of our algorithm can be illustrated by this picture. Look at these three red objects. The three red objects are disconnected in the three-dimensional world, but after the projection, their shadows becomes connected in the two-dimensional world. Now, our algorithm first constructs a good subset of variables. We call this subset of variables M. Then we use global dynamics on projected distribution mu M to draw a random sample from the distribution mu M. Here, mu M is the marginal distribution on M projected from the uniform distribution mu. The global dynamics for mu M is naturally defined. We initialize each variable in M uniformly at random. In each step, we pick a random variable V in M and update the value of V conditioning on the assignment of other variables. The key point is that we only use global dynamics on the projected distribution mu M rather than the original distribution mu. So after the global dynamics, we get a random sample X. X is an assignment of variables in M. Then we sample the assignment of variables in the complement of M from the conditional distribution. Now we need to prove the following result. We need to show that there exists an efficiently constructible subset M such that the following 3 points hold at the same time. First, the global dynamics on the projected distribution mu M is rapidly mixing. Second, the global dynamics on mu M can be implemented efficiently. The implementation is not trivial because in every step, we need to resample XV from the conditional distribution. Such a condition only fixes the value of variables in set M. So computing such a conditional distribution involves a non-trivial counting problem. In general, this problem can be sharply hard. And in the last step, given the partial assignment on M, we also need an efficient way to sample assignment of other variables. Actually, the second and the third points are the same because both of them can be reduced to drawing from the conditional distribution. So we actually have 3 tasks. First, we need to construct a good subset M. Second, we need to prove the global dynamics on projected distribution is rapidly mixing. Third, we need an efficient way to sample from the conditional distribution. We emphasize that the global dynamics is only on the set M and the conditional distribution is conditioned on the assignment of set M. Now, the first step of our algorithm is to construct such a subset M. We call this subset the set of marked variables. This is why this subset is called M. We require each clause to contain at least alpha k marked variables and also contain at least beta k unmarked variables. Such a marking procedure was first introduced by Moicher, but he used it for a very different purpose. The existence of M is guaranteed by Lovász local lemma, and we can use the Morse and Tardish algorithm to construct such a subset M. Next, we need to show that the global dynamics on projected distribution mu M is rapidly mixing. For each step of the procedure, we pick a marked variable V uniformly at random, then we resample the value of V conditioning on the assignment of other marked variables. We remark that all unmarked variables are unassigned in this condition. The local uniformity is the key property for our algorithm. It says that conditioning on any assignment of other marked variables, the marginal distribution on V is very close to the uniform. In other words, we take the value true or false roughly with the probability 1/2. This lemma is proved by Lovász local lemma, as each clause contains at least beta k unmarked variables, and this variable, the white variable in this picture, are unassigned in the conditional distribution. Intuitively, given any assignment of marked variables, we can set the assignment of all these white variables in this picture to get a satisfying assignment. So we can choose its value freely, neither true or false. So after the update, the variable V takes true or false both with a positive probability, which immediately implies the global dynamics on projected distribution is connected. Moreover, we show this global dynamics is rapidly mixing. We show that after O(n) log n steps, the distribution of the output assignment would be very close to the distribution mu(m). The mixing term is proved by the well-known path coupling techniques, and we use the disagreement coupling introduced by Moicher to analyzing the path coupling. The local uniformity property once again plays an important role in analyzing the Markov chains. Now, finally, we need to implement our algorithm. In each transition of the global dynamics, we need to resample the value V conditioning on the assignment of other marked variables. And in the last step, we need to sample the assignment of unmarked variables conditioning on the marked ones. Computing the exact distribution can be sharply hard because it requires us to count the number of satisfying solutions of all unmarked variables. But with high probability, we can still draw approximate samples from these distributions. Now consider each transition step of global dynamics. We need to resample the value V conditioning on the assignment of other variables. We call this assignment xm set minus V. Now, given xm set minus V, a key observation is that some clauses may be already satisfied. For example, we consider this clause. Suppose x1 and x4 are marked variables. If we already know x1 takes the value true or x4 takes the value false, then we know this clause must be satisfied. Satisfied clauses have no effect on the conditional distribution, so we can remove them. The key property is that, with high probability, after removing all the satisfying clauses, the graph is deconstructed into small components of size ODK log m. This is due to the fact that each clause contains at least alpha k marked variables, and each marked variable takes an almost uniform value. So with high probability, each clause can be removed, resulting with the graph only have small connected components. Then we find the connected component C that contains the variable V. That is the yellow component in this picture. Now, to resample the value of xv, we only need to process this connected component C. The advantage is that the size of the connected component is very small. It is ODK log m. But however, if we use the brute force algorithm in this connected component, we enumerate all the assignment in this connected component since they are ODK log m variables, so the running time will be n to the poly dk, which is too slow. So instead, we use the rejection sampling on the connected component C. The variable V and all other unmarked variables, that is the white variable in this picture, neither takes the value true or false uniformly and independently. By Lovász local lemma, we proved that if k is greater than 20 log d plus 20 log k plus 3 log 1 over zeta, then the probability that all the clauses in C are satisfied is at least epsilon over n to the zeta. So we can try the rejection sampling for O2 n over epsilon to the zeta times. Then with high probability, we can draw a sample from the conditional distribution. The advantage of the rejection sampling is that the running time is small, even if d and k is large. Therefore, each transition of the global dynamics can be implemented using this rejection sampling. And in the last step of the algorithm, we can also use a similar method to sample assignment for all unmarked variables. Now, by combining the previous steps, we can obtain our final algorithm. First, we run the more standard-ish algorithm to construct a subset of marked variables M. Then we use the global dynamics on the subset M to draw a sample X from the distribution mu M. Here, for each step of the global dynamics, we use the rejection sampling to implement the transition of global dynamics. And we use the rejection sampling again to draw a random assignment for all the variables in the complement of M. So finally, we can put marked and unmarked variables together to get our final output. The construction of the marked set, the rapid mixing of the global dynamics, and the rejection sampling implementation or individually contribute a maximum error of epsilon over 3. So we can add all the error together to show that the total variation distance between our output and the distribution mu is at most epsilon. The proof is use a coupling argument. We couple our algorithm with the ideal process of global dynamics, so we can add all these errors together to get our final error. Now, to prove the running time of the algorithm, note that the running time is dominated by simulating global dynamics for t equals O(n) log n steps. And in each step, we use the rejection sampling to implement the transition of global dynamics. And we try the rejection sampling for at most r equals O2 n over epsilon to the zeta times. So the total running time is r times t, which is O2 n to the 1 plus zeta. Now let us have a quick look at the counting algorithm. We actually solved the randomized counting problem. The algorithm is required to output a random number z hat, such that with the probability at least 3 over 4, z hat is an epsilon approximation to z. Here z is the number of k-set solutions. Here the number 3 over 4 can be replaced with any constant that is greater than 1 over 2. To reduce the counting problem into a sampling problem, we need to define a weighted CNF formula. Now, suppose we are given a CNF formula phi. We also give a parameter theta. Theta is also called the temperature. We define, for any assignment of variables x, we define the weight of x with respect to the temperature theta as the e to the minus theta fx. Here fx denotes the number of the clauses that is not satisfied by x. So if x is a satisfying assignment, fx equals 0, the weight of x is 1, and if x is not a satisfying assignment, fx is positive, but x still have a positive weight. Now we can define a distribution mu with respect to the temperature theta. The probability of assignment x is wx over z theta. Here z theta is the sum of all the weight of the assignment. Z theta is called the partition function at the temperature theta. So intuitively, the probability of each assignment x in the distribution mu is proportional to its weight wx. Now let's consider some special case. If the temperature theta is 0, then the weight of all assignment is 1, so the partition function is 2 to the n. If the value of theta approach to infinity, then if x is a satisfying assignment, fx equals 0, so the weight is 1. If x is not a satisfying assignment, the weight of x is 0, so the theta is precisely the number of k-set solutions, which is the target of our algorithm. We use the Lovász local lemma to prove the following results for counting. We show that if k is greater than log d plus the constant c, then if theta is O log n, then this theta already gives a good approximation to the number of solutions z. So with this lemma, we want to approximate the number of solutions z. We only need to compute this theta when theta equals O log n. So we use the following non-adaptive simulated annealing. We set L increasing parameters, theta 0, theta 1, theta L, such that theta 0 equals 0 and theta L equals O log n. Here the theta L is precisely the parameter theta in the previous lemma. Now to estimate the number of solutions, we only need to estimate the value of the theta L, and we use the following telescoping product to do this task. The equation holds because the theta 0 is precisely 2 to the n. Now our task is to calculate every ratio in this telescoping product. To estimate the ratio z theta I over z theta I minus 1, we draw a random sample x from the distribution mu in the temperature z theta I, and we calculate a random variable wi as the weight of x with respect to theta I over the weight of x with respect to the temperature theta I minus 1, and we can prove that the expectation of such a random variable wi is precisely the ratio we want to compute. So we can draw random samples from each distributions mu theta 0 to mu theta L minus 1, and we can estimate each ratio in this telescoping product, so we can estimate the number of solutions z. We remark that to do this sampling, we need an algorithm to draw random samples from the weighted CNF formula, but previously our algorithm is designed for draw uniform samples for a normal CNF formula. But this task is not very difficult. We can simply modify our algorithm, and we can draw random samples from the weighted CNF formula. Now, finally, let us conclude our sampling and counting algorithms. The sampling algorithm first mark variables, and we use Lovász local lemma to do the marking procedure. Each clause should contain at least beta k unmarked variables. Then, by Lovász local lemma, we can prove the local uniformity property. With local uniformity property, we can show that the global dynamics mix in O n log n steps. On the other hand, each clause contains at least alpha k marked variables, and with the local uniformity property, we can prove that for each transition of the global dynamics, the connected components is small. So we can use the rejection sampling on each connected component. Then use the Lovász local lemma, we show that we can repeat a rejection sampling for at most O2 n to the zeta times. So combining together, we will get a sampling algorithm in time O2 n to the 1 plus zeta. Now suppose we have the sampling algorithm. Again, by Lovász local lemma, we can use the non-adaptive simulated annealing reduction to get a counting algorithm. So overall, we use the projection, namely marking variables, to bypass the connectivity barrier of the Markov chain Monte Carlo method, So we can use the well-developed MCMC technique to analyze the running time for sampling CNF solutions. And as we can see, the low-vast local lemma plays very important roles in many places in our algorithm. Now, to summarize, in this work, we give fast algorithms for sampling and counting k-set solutions in the local lemma regime. Our sampling algorithm, the running time of our sampling algorithm is close to linear, and the running time of our counting algorithm is close to the quadratic time. Technically, we use projection and the low-vast local lemma to bypass the connectivity barrier of MCMC method. There are some interesting open problems. Perhaps the most interesting open problem is how to push the threshold down to k roughly greater than 2 log d. If we can do it, the upper bound will match the current lower bound, and we can obtain the optimal regime for sampling and counting k-set solutions. Another interesting open problem is to extend our technique to more general distributions, such as the uniform distribution of hypergraph coloring. So we want to obtain a fast algorithm to sample hypergraph Q coloring in the local lemma regime. That's all. Thank you for your listening. And any questions?
Okay, thanks, Mimi, for the nice talk. So I have some, I got some questions from the audience.
Yeah.
I'll ask one by one. So the first one is that this guy says, I didn't understand your rapid mixing analysis. Does the local uniformity property impact global uniformity? In other words, is the projected distribution mu m close to an IID uniform distribution?
No, the rapid mixing means the global dynamics can converge to its stationary distribution very fast. Actually, it's O n log n steps, and the distribution mu m is not an IID distribution. It is the marginal distribution on M projected from the uniform distribution mu. Yes, I did not talk about the detailed analysis of the rapid mixing because it is a very technique. In a high level, we use a technique called a path coupling. Actually, we couple two Markov chains. The two Markov chains start from two initial state, and we show that these two Markov chains will clasp quickly. So this is very technical. If the audience have interest, he can send me an email, and I will give him some very detailed analysis.
Okay, thanks. So the second question from the audience is that the effort to maintain connectivity involves projection from a high dimension to a lower dimension. That violates some property other than local uniformity, or just lose some information.
So I think I not quite understand this question. He asked after the projection, what will happen?
From my understanding, it's like this. By doing this projection, is there any other? Let me see. Some probably other than uniformity. Is there anything more that lose from this projection?
You mean lose from the projection?
Yeah. Like by doing projection, you always lose something, right?
No, I didn't lose. We're doing projection. We did not lose anything because after projection, we will have a marginal distribution. Then we first sample from the marginal distribution. Then given the assignment on these projected variables, we sample from the conditional distribution. So we didn't lose anything.
So that's basically like by doing this projection, it actually makes things more clear, right?
Yes, makes the algorithm more fast. I think.
Yeah. Okay. The third question from the audience is that there's an epsilon to the power of minus zeta in the running time of your algorithm.
Yeah.
What's the exponent of epsilon in previous algorithms?
Okay. in previous algorithms, there are many previous algorithms. For example, let me show you. For example, the classical Markov chain method, the dependency of epsilon is very good. It's log 1 over epsilon. It's very good.
Okay.
And for the deterministic approach, the dependency of epsilon is very bad. It is roughly 1 over epsilon to the poly decay. So to obtain a FP test, we only require our algorithm is polynomially dependent to 1 over epsilon.
Okay.
Actually, in our running time, the dependency to epsilon is 1 over epsilon to the zeta, and the zeta is a very, very small constant.
Okay, cool. So there's another question. In your counting algorithm, what is mu theta?
Mu theta, okay. Mu theta is actually a weighted thing. So to do the counting, we need to define a weighted thing as formula. Namely, the weight means that we will give any assignment of a weight. So if even if X is not a satisfying assignment, we still give it a positive weight. But if X violates many constraints, its weight will become very, very small. If X is a satisfying assignment, the weight is 1. So the mu theta is defined with respect to the weight Wx. The probability of each assignment is proportional to its weight. Intuitively, you can think if X is a satisfying assignment, it has a high probability. If X is not a satisfying assignment, the probability is very low.
Okay, thanks. Actually, I have a very general question. Like you have a sampling algorithm, and you based on that you have counting algorithm. The general question about given a sampling question, can you actually construct a counting algorithm, or is that actually very technical and interesting open problem?
Okay, the famous result given by Jerome, Valiant, and Valirani, they show that for a class of problem that is self-reducible, if you can do approximate sampling, then you can do approximate counting. This include a broad class of problems such as graph coloring, independent set, and many models in statistical physics. And and actually, as far as I know, if you can use the adaptive simulated annealing reduction for any Gibbs distribution, if you have a sampling algorithm, you also get a counting algorithm. But in our work, we use much simple non-adaptive simulated annealing because we can take the advantage of the lowest local lemma regime.
Okay. So let me see if there's any more questions. Okay, if there's no more questions, so that's thanks, Wei-Mi, again. Thanks for your talk.